And good morning, everyone. My name is Dongjiao, and I will present our project of ML and power system modeling tools for LV last mile insights. And it is a subset of our work undertaken to date of our AMLD project. Our project is funded by EPSRC and led by Dr. Bruce Steven. So to begin with, I'd like to talk about some background of our research and our research aim, what kind of problem we are facing and what problem we want to solve through doing this project. So we are focusing on the LV network. Originally, the LV network is just used to deliver the power to each end users. So it is simple and there is no monitoring required. But currently, there are a lot of low carbon technologies, such as low carbon heating, transportation, and solar photovoltaic, that implemented in the LV network. But these low carbon technologies, it may bring excessive load to the network, and if we just leave the network unmonitored, and these low carbon technologies may finally damage the network, and we need to expend a lot of money on fixing the damaged network. So there is a need for us to monitor the LV network currently. Instead of setting monitors everywhere, our AMLD project is trying to find some data-driven approach to help us to monitor the LV network to know the network behavior. So in order to realize this, we need to have a look at what kind of information we know and what we don't know. Basically, we have the GIS system GIS system, which includes the information of the network structure of each specific area. We know how the cables and transformers connected, and we also have studied the relation between load and we have studied between the relation between the load and the network behavior. So, but what information we don't know is the load. We are unclear about the load. So, in order to realize our aim using this information we know and we don't know, we have assembled a process which performs like this. And firstly, we need to choose an area we want to study and we want to investigate, and then we can use the GIS system to help us to know what the network looks like. And then parallel to it, we use the weather information and smart meter readings. And then we will learn the load profiles of each customers inside of this network, and then we feed both of this information to a power flow simulation tool, and then we will obtain the information we want to get to simulate the network behavior, such as voltage, phase angles, losses, and P and Q variables. And this is what we want to finally get. And this can be served as the ground truth for the future predictive models. But the information we know here is the GIS system, and we also have the simulation tools. But what we don't have is the load profiles. So in our current research, we did some research about how to learn these load profiles. And our first research is about if we only consider the solar PV as the only low voltage, as the only low carbon technologies that are implemented in the network. So how can we identify those PV customers? And another problem is that not every customers inside of the network use a smart meter. So how can we estimate those missing smart meter data? So for PV installation identification, and we can't reach this information from the DNOs because the PV installation is not always reported to DNOs. They don't have the complete information. So we need to find some data-driven way to help us to identify PV customers. Our approach is a feature-based classification approach. The data we require is the electricity demand for every customers, and we calculate the statistical features such as mean, minimum, and maximum for each of these customers. And in the feature calculation, we do consider the difference of the consumption behavior of each customers in the weekdays and weekends, and also in different period of a day. And finally, for each seasonal data set, we calculate 63 statistical features in total. But we don't use all of them to feed to the classifiers to do the classification job. Because not every features are relevant features. So we use statistical tests to help us to select those relevant features. And then we connect it to a PCA, a principal component analysis, to help us to further extract the features to get the decorrelated and orthogonal features, and then feed the features to the classifiers. And finally, we found that only a linear classifier will help us to get the very accurate identification results. We have tested our approach on a simulation example. And the data we use is the 1 year smart meter readings of more than 800 residents from the southern and central Scotland, and we simulate the PV generations based on a physics model. And we assume that there are 10%, 20%, 30% of PV penetrations of this area. And we tried our approach on this example, and we found that our approach can help to get very accurate prediction, very accurate identification result, which is above 90%. And taking the 30% of the PV penetration as an example, we can see that if we just use the summer data, the accuracy reaches almost 100% for no matter what kind of classifiers we have used. But for winter data, it seems there is a challenge for area of the classifiers we have chosen. But although all of them can still achieve very accurate results, but the higher accuracy can be achieved by just tuning the hyperparameter of our proposed approach. Our second part of the work is about how to estimate the missing smart meter data using the existing smart meter readings. So our basic thinking is about is to build a statistical model using the observed smart meter readings, and then use this statistical model to estimate the missing smart meter data. So how can we build this statistical model? We basically need two steps. The first step, we clustering the smart meter readings, and then we will get a set of different load patterns, the repeated load patterns. And then in the second step, we model the occurrence of these repeated load patterns by a Dirichlet distribution. And And finally, in this way, we can know the probability for a customers to have each different load pattern. And then this statistical model can be used to estimate the missing smart meter data just by sampling from this statistical model. We have also used a numerical example to test our approach and compared our model with the typical profile model and average model. And we can find that our approach usually can achieve very accurate results predicting the peak load. And we found that for every of these three models, and the accuracy is increasing with the increase of the observed smart meter readings of the customers. And also our model and the average model cannot be used to estimate missing smart meter data if none of these customers have the smart meter readings. But it can be used to, but the typical profile can be used to do this job. So this is basically our main findings, our work currently about this project. And to summarize that, we have found a data-driven way to help us to learn the home picture of the low voltage network, especially when low current technology is implemented. But this is only a very small step. There's still a long way to go. For example, we don't consider the sensitivity of the weather, and also there is a need to further investigate the relation between load and voltage. And so in our future work, we want to continue to investigate machine learning approaches to learn the home picture of the low voltage network just using a very limited data. So at the end, thank you very much for your attention. Any questions?
Thanks a lot. Thanks a lot for this very interesting talk. We are now open to questions. As usual, you can drop them into the chat or even better into the Q&A tab. While people are thinking about how they would like to ask you, I would like to start myself with a question about the limitations of your method. You were very honest in assessing those limitations at the end of your talk, but I was wondering, is that any, let's say, substantial and conceptual limit? Is there something you cannot achieve without monitoring each and every node of the network?
For network, basically, we have everything hidden. And what we only know is is what the network looks like and how cables and transformers connected. But for the load profiles for each of the customers, it is completely unknown, and we need to know this data because not every of the customers, they have a smart meter readings. And because this is based on the latest UK data, it is like more than a half of the customers, they don't have smart meters. So we have a lot of information missing. So, but it is very important for us to know the whole behavior of the network.
Understood. Thank you very much. And I would like also to ask you, what is the immediate next step of your research, and how much further study do you think it is needed before seeing some of your approaches taken to production and used in a real low voltage network?
The next step, we want to now currently we consider the residents and the domestic customers, but we don't consider any of the commercial customers. But in our next step, we want to investigate further about the commercial customers. What are these commercial customers' consumption behavior? We want to learn the detail of these commercial customers. So this is our next step, is what we plan to do.